Uranium enrichment. I'm willing to bet you've heard this phrase a lot in the news lately, and for some pretty serious reasons. You see, this one technology sits right at the intersection of clean energy, global politics, and, of course, international security. It's the key process that can light up an entire city, but it's also the technology that can be used to build the most destructive weapons on the planet. So today we're going to break down what it is, exactly how it works, and why it's still one of the most critical and controversial technologies in the world.
And the reason this is also timely brings us right to this statement, which recently, really shook things up. It comes from Iran's supreme leader, Sayyid Ali Husseini Khamenei, right in the middle of some intense geopolitical tension. This declaration, saying they'll cap enrichment at 60% while denying any plans to go for weapons-grade levels, is pretty much the definition of a high-stakes chess move. And it's the exact flashpoint we're starting with today.
So, that's the big question, right? What does 60% enrichment actually mean? Why is that number so important that it grabs headlines all over the world? And how did this one super-specific industrial process become one of the most sensitive and closely guarded technologies on the entire planet? Well, that is exactly what we are going to unpack right now. Okay, let's get into it. Here's our game plan. We'll kick things off with the 60% question to get the context. Then we'll dig into the science with what is uranium enrichment and the tech behind the 3 paths to purity. From there, we'll look at the big dilemma in power plants or proliferation, see who controls the atom around the globe, and wrap up with nuclear's double-edged sword. It's a straight line from the news headlines to the hard science and back to what it all means for the world.
All right, let's start with Section 1. The 60% question, and the nuclear flashpoint that's put this whole topic right back in the spotlight.
So what's going on is pretty complex. On September 23, 2025, Iran announced it was firing up its enrichment process again, and this came after its nuclear sites were reportedly targeted in attacks. In response, Iran's leadership said, okay, we're enriching up to 60%, but we're stopping there, nowhere near the 90% needed for a bomb. But here's what has the international community so worried. First, there's no obvious peaceful civilian reason to enrich uranium to 60%. And second, analysts figure Iran probably has about 400 kilograms of this stuff stockpiled. Now, if they ever decided to push for more, that material could be turned into enough weapons-grade uranium for about 9 or 10 bombs. And of course, this is a major breach of the 2015 nuclear deal, the JCPOA, which limited Iran's enrichment to just 3.67%.
To really get why this is all so tense, we've got to peel back the layers and get down to the science. That brings us to Section 2. What exactly is uranium enrichment? The best way to think about it is as the ultimate atomic sorting problem.
At its heart, the idea is pretty simple. Uranium enrichment is just the process of increasing the percentage of a very specific kind of uranium atom, an isotope called U-235. This one little isotope, well, it's the magic ingredient. It's the key that unlocks the massive energy inside the atom, for both good and bad.
So, to understand this, you need to meet the 2 main characters in this story. On one side, you have uranium-235, the fissile star of the show. It's unstable, and when a neutron hits it, it splits apart. That's called fission, and releases a huge amount of energy. This is the guy you need for both power plants and bombs. On the other side is its much more common, much more boring sibling, uranium-238. It makes up almost all natural uranium, but it's stable and doesn't split easily. So, to get a nuclear reaction started, you have to separate the rare U-235 from all the abundant U-238.
And here's the real challenge. This number, 0.7%, is everything. In any chunk of uranium you dig out of the ground, only 7 out of every 1,000 atoms is the useful U-235. The other 993 are U-238. So the entire, incredibly difficult goal of enrichment is to boost that tiny 0.7% up to a much more useful level.
Okay, so if it's just a sorting problem, why is it so ridiculously hard? Why can't you just use some chemical reaction or a simple filter? Why is building an enrichment facility considered such a massive technological achievement for any country?
Well, the problem is that these 2 isotopes are basically identical twins. Chemically, they act exactly the same, so you can't use chemistry to pull them apart. The only difference is a tiny, tiny variation in their weight. U-238 is just 3 neutrons heavier. That's a mass difference of less than 1%. This means you're forced to use these incredibly complex and energy-guzzling physical methods that can exploit that tiny weight difference over and over and over again.
So how do you actually do it? Let's jump to Section 3.
3 paths to purity. We're going to look at the main technologies that have been developed to solve this atomic puzzle.
First up, the original old-school brute force method, gaseous diffusion. This is the tech the Manhattan Project came up with. The idea is you turn uranium into a gas, uranium hexafluoride, or UF6, and then you force that gas through a barrier with microscopic holes. The lighter U-235 gas molecules move just a tiny bit faster and squeeze through the barrier a little more often. But the effect is so small you have to do this in a massive series of stages, often more than 1,000 times just to get to reactor-grade levels.
Now, the technology has come a long way since then. Gaseous diffusion is pretty much obsolete now, mostly because it uses a mind-boggling amount of energy. The main method today is the gas centrifuge. It works by spinning that same UF6 gas at insane speeds. Centrifugal force pushes the heavier U-238 to the outside wall, while the lighter U-235 concentrates near the center. It's way more efficient, using something like 50 times less energy. And on the horizon, we have the future, laser enrichment. This next-gen tech uses super-precise lasers to zap and excite only the U-235 atoms, letting them be separated. It could be even more efficient, but it's not really out there in the commercial world just yet.
Now, the incredible difficulty and sophistication of this technology brings us right to its central challenge, the reason it's so closely watched. Section 4, power plants or proliferation, the dual-use dilemma. The very same facility can make fuel for peace or material for war.
So what really matters is the final concentration of U-235. For peaceful stuff, like generating electricity for a city, most nuclear power plants need what's called low-enriched uranium, or LEU. This is typically enriched to about 3 to 5% U-235. This is the workhorse fuel of the entire global nuclear energy industry.
And now we're back to that number from the headlines, 60%. This level is way beyond what you need for a normal power plant. Now, sure, some research reactors or naval ships use higher levels, but 60% is seen as a really dangerous line to cross because there's no clear peaceful use for it, and it means you're technically just a hop, skip, and a jump away from being able to make a weapon.
And here it is, the finish line for a weapons program. Uranium enriched to 90% U-235 or higher is officially weapons grade. Now, the absolutely crucial thing to understand here is that the process isn't linear. The hardest part, where you spend most of your energy, is getting from that natural 0.7% up to the first few percent. The jump from, say, 20% to 60% and then from 60% to 90% is technically much faster and easier. So being at 60% means you're already most of the way there.
So with stakes this high, who actually has this technology? Let's move on to Section 5 and take a look at the global map of nuclear capability. Who controls the atom?
The whole story really starts back in the 1940s, with the massive scientific and industrial effort of the Manhattan Project in the US, which basically invented gaseous diffusion on an industrial scale. Then, during the Cold War, the tech started to spread as other countries developed their own weapons programs. But since the 90s, the game has changed, and the much more efficient gas centrifuge has become the global standard for both commercial fuel and government programs. If you look at the commercial enrichment world today, one thing becomes crystal clear. Not many people can do this. It's concentrated in the hands of just a few major players. Russia's state-owned Rosatom is the world leader by a pretty wide margin. They're followed by Urenco, which is a European group, and then China's National Nuclear Corporation. It is a very exclusive club.
And all of this, the science, the tech, the history, the politics, it all brings us to our final section, where we look at the core problems and what might be coming next. Section 6, Nuclear's Double-Edged Sword and the Future of Enrichment.
The challenges here are just immense, and they're not going away. The price of admission is astronomical, billions and billions of dollars. The risk of proliferation is that constant shadow in the background, requiring non-stop monitoring. The facilities themselves are major national security sites. You've also got the environmental issue of what to do with all the leftover depleted uranium. And then there's the constant geopolitical tug-of-war between a country's right to peaceful nuclear energy and the world's need for safety.
And this really is the big question for the future. We've seen the tech evolve from these huge, power-hungry plants to much sleeker centrifuges. The next generation, laser enrichment, promises to make the whole process even cheaper and maybe even easier to hide. So as the barrier to entry gets lower, the pressure on our global systems, on our treaties and inspections, is only going to get bigger. Can our rules and our diplomacy evolve as fast as the science?
And that's our look at uranium enrichment. It truly is a cornerstone of the nuclear age, with all of its incredible promise and, of course, its peril. Now, to really lock in what you've learned and dig into these details, make sure you visit the link in the description. We've got our detailed notes and a quick revision mind map all ready for you there. Thanks for joining us.